Good evening and welcome to the May 2025 Madison DX Club feature program. And to introduce tonight's speaker, Bob W9EWZ. We'll introduce him.
Well, good evening, everyone. Tonight we have Roger Harrison, VK2ZRH with us. This is the third presentation that he's given to the Madison DX, and every one of them has given us a lot of food for thought. Roger packs a whole lot of science into his presentation. He's a very experienced person in the area of propagation, both in research and as a career for the space weather prediction, the equivalent of the Space Weather Prediction Center in Australia. Roger's also widely published. He's the editor of a couple of amateur radio magazines in Australia. So, Roger, welcome. We're so happy to have you back. And please go ahead. Begin whenever you're ready.
Okay, well, good evening to you. It's morning here, coffee time. But all right, I will get up the presentation and share the screen. Okay, presentation of the meeting of the Madison DX Club, again, Wisconsin, USA, May 14, 2025. So the subject this time is summer solstice short path propagation on 50 megs, otherwise known as SSSP. And my talk today covers testing Higasa's hypothesis. That's a grand title. Let's get a little background first. Although Bob did introduce me, just in regard to this project, which principally involves sporadic E. I spent many years in my previous careers, but specifically through the 2000s, gathering a lot of papers and presentations and organising them into categories and all the rest of it. You see that stack of folders on the desk there? I still have those here in my room in Queensland now. But there's more than 1,000 papers on the subject, which I've been through meticulously, sometimes over and over. And you can see a manual or a collection book on the right-hand side from Dubis. I've written on this subject for Dubis magazine, which is a German quarterly publication. So SSSP was proposed by Han Higasa J1BMJ in the Japanese journal CQ Ham Radio in 2006. This publication was brought to my attention a couple of years later when an English version became available in PDF online, which was most handy. And I looked into it very carefully because the subject gets mentioned on forums, on the air, at conferences, and anywhere else amateurs talk and share ideas and experiences. So it's a well-known subject and remains a popular idea, even this amount of time later. So I looked into it It was an intriguing proposal. It really is. So it's based on contacts that Higasa made between Japan and the USA and Europe during the summer solstice period, which is, the height of 6 meter DX. So here's a map that I produced, just generally illustrating the paths that he worked over a period of several decades, extending out to 10,000 kilometres mostly, and a little beyond that. It looks like that because of the span of population rather than any peculiar characteristic of propagation. That's just a standard azimuth equidistant projection centered on A, which is Chiba, where Han lives. So here is the SSSP from the North American perspective. So gathering reports from W0WI in central USA, I plotted a number of chief paths, and it clearly crosses the high latitudes, whether you define that as 60 degrees north geographic latitude or 60 degrees north geomagnetic. Either way, it crosses the polar region. I've outlined a number of places there in Alaska. One place in particular, Poker Flat, where the US government operates vertical incidence atmospheric radars. The same goes for European institutions which operate off the coast of Norway. So, what are the characteristics? This is the first three major characteristics he set out. Is seasonality. Contacts are reported during the summer months and centered on the solstice, which of course in the northern hemisphere is 22nd June. But generally daytime paths. There's a diurnal thing to it. Stations at one end of a path make contacts in the morning local time, working stations at the other end of the path in late afternoon or early evening. So the paths are primarily daylight end to end. That's just a matter of the geography. Kind of a general east-west direction. Now, he observes that the paths are confined to the same hemisphere. Japan, to North America, Japan to Europe, etc. North America to Europe. The shorter path into KL7 is around 5,000 kilometres. But the terminals can include the Middle East, North Africa. And figure 1 there is the map that I just showed previously. So there's more. Azimuths. He observes the path azimuths are on or close to the Great Circle path between stations, which is interesting. Openings may last for short periods, up to 6 hours, and the areas open are spotty. In other words, a station will be received by someone and not by someone else in the same general area, a few kilometres away, which which speaks of a focusing effect. The signal characteristics range from very weak through to very strong, with slow QSB and no noted distortion. He had some interesting comments to say about that. Solar characteristics. The annual openings do not appear to be influenced by the solar cycle. And the openings, he observes, are 50 megs only, but not on higher emitter bands or lower emitter bands, which is a pretty brave observation. So Higasa advanced, this quite brave hypothesis in the best traditions of inquiry and self-learning, which is at the heart of amateur radio, and the ITU definition, which we all know by heart. So let's look at his propagation proposal in the vertical plane. This is a redrawing of what appeared in CQ ham radio in 2006. So he's got all these control points, A, B, C, D, E, etc. And what he calls the PMS E region, polar mesosphere summer echoes region. And he proposes that it's like a whispering gallery right through from end to end. He doesn't think there are any ground reflections occurring at all. So great circle paths up to 10,000 plus kilometres pass over the high latitudes, as I observed earlier. So here's his previous map. And he asked, wouldn't 4, 5 or 6 hop sporadic E have too much loss? So he rules out sporadic E on this basis, that it would be too lossy for multi-hop sporadic E of that sort of order. And he looks for atmospheric phenomena at high latitudes to support 50 megs over the polar paths. So he went hunting for ways and means in the atmosphere. And he found a correlation with polar mesosphere summer echoes, which occur in the atmosphere in the altitude range 80 to 90 kilometres. So here's a vertical radar plot from Svalbard Islands off, well inside, these islands off Norway, well inside the Antarctic Circle. So you get these hazy reflections over a period of time. Here is about from 1500 to 2200, good 7 hours. And so they persist for some time, and multiple layers persist. They're detected by polar latitude atmospheric research radars, recording echoes from the troposphere to the mesosphere, in other words, the D region. And one of these looks like this. This is an array of 433 yagis of Andes in Norway. All of them are phased and can be operated to steer the beam. It's quite a complex facility. Now, these MST radars run megawatts on bands from 50 megs to 1 gig. And of course, you can see huge antenna arrays. There are some that are larger. acronyms again. The Marsi antenna, that antenna you just saw, is a different view from the ground. So Yagi after Yagi, ranked and arranged in rows. So the echoes arise from low-density aerosol layers. In other words, sort of like very thin rain, except that, of course, at that height, the temperature is very low, and it consists of minute ice particles. Here's one from Andine, off Norway, running for some hours. And it's a persistent layer, as you can see, but very thin, and between, pretty much confined between 80 and 90 kilometres, with the peak around 85 kilometres altitude. So this is the 53.5 meg radar at Andine's, as I said, which is inside the Arctic Circle. Occurs between 80 and 90 kilometres, peaking at 85 kilometres, as I observed. So what's going on there? So if we look at the occurrence rate, which are the numbers across the top, and look at the water vapour frost point and the atmospheric temperature, which declines quite steeply through that region. But once it reaches the D region, around 90, about 88 kilometres right through 90, it begins to rise again, and it rises right through the ionospheric region. So the green curve shows the occurrence rate of PMSE, and the blue curve shows noctilucent clouds, which are visible clouds that occur in the Arctic regions. That measurement was made with a laser LiDAR range detector. Noctilucent clouds are visible in the afternoon, evening, when the sun is at a very low angle. There we go. It's not going to move on. There we go. So PMSE and noctilucent clouds are related. Now here's a view of some noctilucent clouds. As you can see from the previous diagram, their occurrence ranges cross over, but peak at different altitudes. These NLC, noctilucent clouds, also are very small aerosol ice crystals, but rather larger than the ones involved with PMSE. So it has a seasonal occurrence rate, which is favourable to Higasa's hypothesis. So here we are. I went looking for this and looked it up for the Northern Hemisphere and the Southern Hemisphere. Australia runs a high power radar at Davis Station, which is located on the coast of the Antarctic continent at longitude below India. And that radar operates at 1.94 megs and records PMSE and other phenomena. It was installed by a friend of mine, Dale, VK2ZRH, some years ago. So PMSE showed promise, but how would signals reach the region? That's the question. So here we are with Higasa's hypothesis about the propagation path. So just look at that once again. We got the various control points. So he proposes, firstly, deflection in the F1 ionosphere at A or E, and to reach B or D without intermediate ground reflection. And thirdly, propagation via a whispering gallery along PMSE in the region around C. So this is his principal hypothesis. So here's the geometry of what he proposed for 1 and 2. So we look at the first and second control points. And he proposes that that control point is in the 90 to 100 kilometre region, which is basically in the E region. Might be sporadic E, but he's saying that the F1 region will turn a 50 meg signal towards the horizon and propagating forward without intersecting the ground before it reaches control point 2. So let's take a look at control point A. So here's the electron density of the F1 layer globally and over the solar cycle. I got this from a publication about F1 region behaviour, which is written by my old boss at the Ionospheric Prediction Service. So it's not terribly promising. You don't. The best vertical incidence reflections are at 5 or 6 megs. To deflect, just to deflect 50 megs to the horizontal would require electron densities about twice that. So there you got it for the high sunspot cycle and the low sunspot cycle, and across geometric latitudes from equatorial to high latitudes. Doesn't quite exactly correspond with the geographic latitudes, but this is propagation we're talking about. So a closer look at F1 near A over Japan one summer. And the summer that he published his paper. So this is to the north of him at Wakanai. And in the period at local mean time, yes, you get a peak in the middle of the day, but it's not terribly dense layer. So it's not going to do much for your 50 meg signal. The comment here is, got to think about that. Here he is, F1 near A over North America. The nearest one I could get was a spring 1990 for Wallops Island, which I presume you people know the location. There's a northeast USA. And again, the big dots are the mean values, and the bar, of course, shows the variation. Kind of promising, but not all that promising. Again, the peak is at local mean time, noon. which is what you'd expect because the sun is creating the ionosphere. So, some conclusions. The primary points. Firstly, the propagation path fails at A and B because the F1 region electron density is too low to support deflection of 50 megs RF at necessary angles. Nobody works even short distances, let alone DX, by F1 reflection. And 2, PMSE cannot support 50 megs because the low density nanometer-sized ice crystal layers, while producing echoes on megawatt power 50 meg vertical radars, can have little effect on 6 meter band amateur signals propagating at low angles. The mistake I think that Higasa has made was that the measurements he looked up for PMSE were at 50 megs, but that's vertical incidence and very high powers. And he's conflated that with lateral propagation, which is a bit of a mistake. Anyway, he had to try. Somebody had to do so. So subsequent work has shown that its SSSP is multi-hop sporadic E, and I've spoken about this before in a presentation to you. However, Dubus magazine, which I mentioned earlier, you can download this copy, which my paper on the subject, running quite a few pages, complete with illustrations that I've just run over with you. It's all in there. You can download it from that web address. So we've come to this point. That's the end of my presentation. Do we have any questions?
Please, anyone with questions for Roger, go ahead.
Yeah, can you hear me? Yeah, I guess I can. I have a question. Are you saying that SSSP is not the, you conclude that it's not SSSP, but rather multi-hop sporadic E?
It is.
Okay, because there was I read an article that was produced by a man from Portugal that I've worked from the West Coast here, and he also pointed out the same, that that he is working stations in different hop zones, right, across the. I don't know if you ever saw that presentation, that article. And the second thing is then, is there chordal E layer propagation?
I'm sorry, that last question. Is
Okay.
there?
You pointed out a non-multi-hop situation where there were chordal hops between that never returned back to Earth. Is there such a thing as that in sporadic E?
Probably not. Is my my answer to that.
Okay.
There is. You do get chordal hop propagation, but over very short distances, and running from ripples in a sporadic E cloud, and so the signal propagates from crest to crest in these ripples, which has the impact of, firstly, focusing the signal so that you get a focal point on the ground, and that increases the signal strength. But away from the focal point, it's like shining a flashlight.
Spotlight propagation. Okay, then how is it that there isn't a huge amount of attenuation because of multi-hop?
Well, firstly, the loss from ground reflections is quite small, the signal spends very little time in the E cloud, and the propagation loss there is small. It's only a couple of dB per skip. I've done a link loss budget for a number of paths that have been observed and recorded, and you can do that quite readily, and you have to estimate some things, but you can include all of that in the loss link budget, and the loss doesn't reach anything too great. In fact, in some instances, you get, of course, because of focusing, you get what would appear to be some gain. So it's better than free space path loss.
Yeah, I was going to say, yeah, so you could just take the multi-hop path length and then equivocate it to a one path, single path, and calculate the free space path loss from that. And you're saying that it's better. It's like having reflectors in the sky that are reflecting, you know, more flux density than you would with just a regular spreading loss.
Yes.
Okay.
Not all the time, but yes, you can. There are instances where I've gained the material that has happened.
Yeah, we've worked from the West Coast. We've worked into as far as out as Ukraine, and also, that's another issue, and also easily to Japan and out as into Southeast Asia and China from here. We think it's during the sporadic E season, so we think it's multi-hop. We've had openings when the solar flux index was way high in the 230s, something like 220, and we have worked long path into into Indian Ocean. I'm trying to recall what the Reunion Island, for instance, from here, and that's occurred a couple of times. And that's another question. You said there is no F propagation on 6 meters.
Oh. Well, yes, there is.
Okay.
Particularly if you cross the geomagnetic equator, because you can get TEP assisting it,
Yeah.
or you can get equatorial sporadic E, which is a daily occurrence, I must add, and supports propagation up to around 70 megs. It doesn't occur by the usual wind shear. It's a sort of a rearrangement of electron density, plus and minus of a few degrees of the geomagnetic equator.
Right, the electron bulge. Okay, thank you.
Yeah, well, yeah, no, but yes, there's those. The equatorial ionospheric anomaly, but they're plus or minus 20 degrees. There's this narrow range along the geomagnetic equator where you get what's called equatorial magnetic sporadic E, which is again a thin, narrow layer, and it's brought on by winds and cross equator winds and electric fields.
Okay, you mentioned winds. I talked to somebody just recently. We had a discussion. they believe that sporadic E is caused by micrometeorites and that it's more reflective than refractive. I don't know. This I might be getting off subject, but
The
and he said that
micrometeorites are short-lived. Well, yeah, so far as we're aware of them, on the ground. However, the atmosphere receives tons and tons of meteors every day. And so, and of course, it breaks up in the ionosphere into molecules, which then get blown around and attract charges or remain as ionized, and then that's all swept into with wind shears. It's all swept into a cloud of metallic ions. That's what is in sporadic E, not atmospheric ions. Metallic ions are very long-lived, so they're very easy to ionize, but they take a long time to recombine.
right.
I'm talking hours, hours to days.
Right, so that's why you can see a sporadic E cloud move from basically from east to west is what I've noticed that over the day the cloud will move across it, and it's wind shear that is causing it to move. So it has to be something. He also mentioned. I remember it was Frank Donovan that mentioned it, that when you have high solar flux index, it's not the solar flux index, but it's the heating of the atmosphere that causes dispersal of the electron clouds, and that's why when you have a high solar flux index, the energy that's poured into by the sun does kind of suppress sporadic E. We haven't had much sporadic E in the past 2 years here. It's been a lot more short-lived than during the low part of the solar flux index, solar cycle, I mean. So when the solar flux was around 100, we were working Europe, just about every day during the sporadic E season.
You're talking here of the heating effect of the sun on the atmosphere. That's called the thermal tide, which of course will expand the atmosphere on the sun side. So during the day. However, the wind systems which bring on the wind shears will shift patterns away in all directions, away from, shall we say, the subsolar, what's called the subsolar point in the geography. So you're in a fixed point, you're working other people in a fixed point, but the sporadic E moves somewhere else. You're lucky. You understand what's going on there? It's not that the sporadic E is disappearing. It's that it's not moving past your paths.
Yeah, when you say a subsolar point, you're saying that the incidence of the sun onto the Earth, that point has more heat, and then it's driving everything away from that.
Yes. So the atmosphere expands, and that expansion, of course, becomes a wind which moves, north, south, east, and west in all directions. That's a daily phenomena, and because of the increasing output of the sun at solar maxima, it changes that phenomena.
Yeah. And one more thing, when we worked to Europe, we were having really good propagation in Europe a few years ago. It started like 10 minutes to 7 in the morning. I kid you not. And we had workstations I'm trying to recall, somewhere in Great Britain as late as 6 p.m. at night. And it did tend to move from east to west. So we'd start working Europe, and then it would disappear in midday, and then later on in the afternoon we're working Asia. That was pretty prevalent.
Yeah, that's the daytime accumulation of wind shears, which produce the sporadic E. It has a diurnal. It actually has two diurnal peaks. One across noon, yeah, for obvious reasons, and then it dips in the afternoon, and there's a minor peak in the early evening. So when you put it all together, this is the effect that you're experiencing.
Yeah, it's amazing. Yeah, thank you.
Pleasure.
That was a great addition to our program right there. Any other questions for Roger? Well, hearing none, I'd like to just once again extend the club's thanks to Roger for all of the programs that he's done for us, and I hope in the future there'll be more. These are always both technical and practical. We really enjoy that. We will have this up on our webpage, or excuse me, on our YouTube channel in the next couple of days. So feel free to review it, share it with your friends or club members from other clubs. And any final word from anyone? All right, everyone have a good evening. We'll see you next month.
Thank you very
Roger.
much.
Thank you.
Cheers.